Welcome to the core architecture and state management phase of our journey. Here we pivot from theoretical paradigms into the mechanical structure that brings agentic workflows to life. During this phase of the course, your primary objectives are to define the operational roles of nodes and edges and to orchestrate parallel execution using specialized supersteps. You will also learn how to implement state graphs for robust shared memory while configuring reducers to maintain absolute data integrity during highly concurrent operations. We begin our exploration by examining the fundamental building blocks of cyclical workflows, focusing specifically on nodes, edges, and how they interact to create intelligent execution paths. Let us start by looking at nodes, which serve as the fundamental operational units where actual computational work occurs within our architecture. If you picture a sprawling factory floor, the nodes are the specialized robotic workstations executing specific tasks. In a graph architecture, nodes typically represent individual Python functions or fully autonomous agents possessing specialized tools. When activated, a node receives the current global state of the workflow as its primary input. This state payload acts as the absolute truth for that moment, containing all previous decisions and gathered data. The node processes this information, executes its designated logic, and returns specific state updates. These updates modify the shared workflow memory, appending data to ensure the system is aware of newly generated insights. By functioning as independent state-aware actors, nodes form the bedrock of orchestration. To make this highly practical, we can map the function of a node directly to concepts you use in robotic process automation. You can think of nodes as operating very similarly to encapsulated workflows or custom activities within platforms like UiPath. Just as a custom activity operates as an isolated container with a specific execution scope, a node encapsulates a distinct block of business logic. Both paradigms require clearly defined input parameters and yield strictly defined output schemas. When you build a custom activity, you define your arguments in and out to ensure data flows predictably. Nodes operate on the exact same principle, ingesting the global state and outputting an updated dictionary. This similarity means nodes inherently support modular design. A well-constructed node can be deployed across multiple graph structures, just like reusable automation components. While nodes represent the active workers in our system, edges serve as the essential pathways controlling the exact sequence of node execution. If nodes are the workstations on a factory floor, edges are the conveyor belts connecting them. Their primary responsibility is determining exactly which node must execute immediately after the currently active node finishes its task. Beyond simple sequencing, edges facilitate the critical transfer of the updated state payload from one actor to the next. Without this seamless handover, the subsequent node would have no context of the work that was just completed. By defining these connections, edges establish the overarching topology and directionality of your entire workflow. They dictate whether a process moves in a straightforward sequence, branches out into parallel operations, or loops back upon itself for error correction. Let us look at the data movement methodology to understand how state payloads travel through this architecture. The rule is that payloads must move continuously along edges to ensure contextual memory remains perfectly current. Imagine node A extracts data from a financial document. It completes its logic and returns a dictionary of state modifications, like adding an extracted invoice number. The orchestration framework then applies these updates to the master state object, merging new data with the existing payload. Once updated, an edge steps in to route this freshly modified state object seamlessly to node B, which might validate the invoice against an enterprise database. This continuous cycle of execution, state modification, and edge routing creates a highly reliable central data pipeline. Up to this point, we have discussed standard edges, but the true cognitive power of this architecture is unlocked through conditional edges. Conditional edges introduce dynamic decision-making directly into the execution pathway, moving us far beyond rigid linear flowcharts. Instead of blindly following a statically programmed route, a conditional edge pauses to actively evaluate current state data. For example, It might analyze a newly updated sentiment score or check if an error flag was raised during the previous node execution. Based on this evaluation, the conditional edge executes customized routing functions to determine the most appropriate downstream node. This capability is absolutely essential for enabling complex logic flows, such as dynamic human approvals or intelligent document routing, thereby mimicking complex reasoning perfectly. The ultimate expression of these components working together is the creation of self-evaluating revision loops. Here, cyclical pathways allow agents to autonomously critique and systematically improve their own outputs. By routing a conditional edge back to a previous node based on a specific evaluation, you create a powerful iterative loop. Picture an orchestration designed to draft legal contracts. The initial node generates a draft and passes it to an evaluator node. The evaluator node scans the draft against compliance rules and identifies a missing clause. Instead of failing, the conditional edge routes the state payload along with the feedback directly back to the drafting node. The drafting node incorporates this targeted feedback, refines the document, and submits it back to the evaluator, repeating until a defined quality threshold is achieved automatically.